Dear students, very good afternoon. Now we are going to see one important problem. Before that, we are going to see an important note. The note is, so the note under Taylor series, under Lawrence series. See, take down a note. Simply, I can tell one thing. Instead of Taylor series expansion or Lawrence series expansion, we can use binomial series expansion. Okay, yes, yes, Taylor series and Lawrence series expansion are unique. It is not necessary to apply the theorem or apply the formula. So sometimes we can directly use binomial series expansion. So notice we can use binomial series expansion instead of Taylor series and Lawrence series expansion. Instead of Taylor series and Lawrence series expansion, yes, they are unique in the given region. Unique in the given region. Okay, so this is going to be our third problem. Okay, so where we can apply binomial series expansion. So the question is, obtain Taylor series to represent the function z square minus 1 divided by z plus 2 into z plus 3 in the region modulus of z less than 2. Modulus of z less than 2. Okay. Now they have given solution. See the solution. See, our previous problems are very easy. Expansion of e power z, log of 1 plus z, or 1 by z minus 2. So the expansions are very easy. Sin z, cos z, f of z will be. So the expansions will be easy. But here we are having so many terms. In numerator we are having z square minus 1, denominator we are having z plus 2, z minus plus 3. The problem here is they have mentioned the region for f of z, that is z square minus 1 by z plus 2 and z plus 3 about the region modulus of z less than 2. The function is varied only within the region modulus of z less than 2. So for the points z equal to minus 2 and z equal to minus 3, the analyticity will be lost. So f of z is not analytic at z equal to minus 2 and z equal to minus 3. Okay, so in such cases we can go for binomial series expansion instead of going for Taylor series and Lawrence series expansion, because both Taylor series expansion and binomial series expansion or Lawrence series expansion, binomial series expansion will give us the same kinds of expansion. Okay, now consider, now the function is very complicated one. I am going to break the complexity, I am going to break the toughness in this question. What is given? F of z equal to z square minus 1 divided by z plus 2 into z plus 3. So how it can be written? It can be written as z square minus 1 divided by z square plus 5z plus 6, which is equal to z square minus 1 divided by say, kindly wait, this has to be done after solving this. I'm going to solve this division. Z square minus 1 divided by what is given, z square plus 5z plus 6. So I can take 1, but before that you have to know z square minus 1 can be written as z square plus 0z minus 1, so that I can easily write z square below z square and 5z below 0z and plus 6 below minus 1. So now subtracting will give the result. The remainder is minus 5z minus 7. So, okay. So now this function, see what function? This function can be simplified as follows. But before that you have to know one thing. If I am going to divide 7 by 3 means how I can write this. So 7 divided by 3 will give 2 as the quotient and 1 as the remainder. So it can be written as 2 1 by 3, which is 2 plus 1 by 3. On taking LCM, 2 3s are 6, 6 plus 1 7, 7 by 3 will give the same result. In the same way, I am going to write this function. That is, first thing is we have to write the quotient. Okay, let's write quotient. Quotient here is 1. The second thing is we have to put the plus sign. Okay, put plus sign, and after that we are having the remainder. The remainder is minus 5z minus 7. And the last thing is the term which is used to divide the numerator. That is, we are having a divisor here. That is, we are having z square plus 5z plus 6. Is the function, is the given function is now simplified? No, it is not fully simplified. So I am going to bring it back to the original form of the denominator. That is, f of z will be 1 plus minus 5z minus 7 divided by z plus 2 into z plus 3. Now see, minus 5z minus 7 divided by z plus 2 into z plus 3. Now consider it, since the function is not now fully simplified, I am going to simplify this. So now consider minus 5z minus 7 divided by z plus 2 into z plus 3, that is equal to a divided by z plus 2 plus b divided by z plus 3. A divided by z plus 2 plus b divided by z plus 3. So this is called the reducing the given function into the form of partial fractions. So by this we obtain a of z plus 3 plus b of z plus 2 equal to minus 5z minus 7. So now put z equal to minus 3 and z equal to minus 2. By putting z equal minus 3, we get minus b equal to plus 15 minus 7, that is equal to 8. By putting z equal to minus 2, we get a equal to 10 minus 7 equal to 3. So the answer is A equal to 3 and B equal to minus 8. A equal to 3 and B equal to minus 8. Okay. So we can write the f of z. We can write the f of z as f of z equal to, so before that I shall write here, this is equal to 3 by z plus 2 minus 8 by z plus 3. So f of z is 1 plus 5z minus 7 divided by z plus 2 into z plus 3, that is equal to 1 plus 3 divided by z plus 2, then minus 8 divided by z plus 3. So they have given the region less than modulus of, so this the modulus of z less than 2. So they have given modulus of z less than 2. If it is modulus of z less than 2 means what will happen? Modulus of z less than 2 means modulus of z by 2 will also less than 1, as well as modulus of z by 3 will also less than 1. So it will make our further simplification. Since modulus of z is less than 2, if I bring it to denominator, it will be less than 1. So increasing denominator will reduce the quotient value. So I'm increasing denominator 2 to 3. So definitely, since division by 2 is less than 1, then obviously division by 3 also less than 1. So we get I'm going to do this, f of z equal to 1 plus 3 divided by, I'm going to take this 2 outside. If I take this 2 outside means I will get z by 2, okay, z by 2 plus 1, z by 2 plus 1 minus 8 divided by 3 of z by 3 plus 1. So why I have made these things means, so we have told in the beginning we can make use of binomial series expansion. What is binomial series expansion? So the binomial series expansion is I shall give you an example. Okay, the binomial series expansion is very easy. Just kindly take it down. Here I am going to write, see, please write, listen carefully. I am going to write, just a minute. Okay, so here I shall tell you this example later. The formula, the structure of the binomial series expansion will be a plus b whole power n. It will involve two terms, one term and another term, and it will have the exponent n. Okay, so a plus b whole power n can be written as sum of all the factors. Okay, sum of all the factors k equal to 0 to n, k equal to 0 to n, n c k. So it can be written like this, n c k x power n minus k into, sorry, it will be actually a power n minus k into b power k. Okay, a plus b whole power n can be written as summation of k equal to 0 to n. The same thing can be written like this, n c k, a power n minus k, b power k. Okay, so this is the binomial expansion. Now I am coming back to an example. Okay, example. Okay, as an example, you are very familiar about 1 plus x. See, 1 plus x whole power n means what will you get? 1 plus x, here n equal to c n c k equal to 0 to something. So if I put n k equal to 0 means I will get see what can I do. So I putting 1 plus x whole power minus 1. Okay, the expansion is 1 minus x plus x square minus x cube plus etc. Okay, so if I take 1 minus x whole power minus 1 means it will become 1 plus x square plus x cube plus etc. Okay, so all these expansions are arising because of this original formula. Okay, here n is minus 1, here also n is minus 1. Here I am having two terms, one is a and x is b, one is a and another x is minus x is b. Okay, so in such a way we can get a binomial expansion of anything. So in any case I am having one term as my 1, which makes the expansion very easier. So I have brought these 2 to the denominator by taking these 2 common outside. I have brought these 3 in order to make this as 1, so that I can take these 3 outside. Okay, so but you should not take the z to the denominator of the denominator. Okay, that you have to keep in mind. Okay, now this f of z can be written as 1 plus 3 by 2 into 1 plus z by 2 whole power minus 1 minus 8 by 3 into 1 plus z by 3 whole power minus 1. I am expanding this as f of z equal to 1 plus 3 by 2 into 1 plus z by 2, 1 minus z by 2, okay, plus z by 2 whole square, okay, z by 2 whole square, I am going to write z by 2 whole square. So see z by 2 the whole square minus z by 3 whole power n, sorry, whole power 3 plus etc. minus 8 by 3 of 1 minus z by 3 plus z by 3 the whole square minus z by 3 whole power 3 plus etc. Okay, now 1 plus 3 by 2 of, how to write this expansion? This expansion can be written as summation of, since we are having plus minus alternatively, we will have minus 1 power n. Okay, and z by 2 is common everywhere. I can put z by 2, z by 2 whole power minus 1 power n, z by 2 whole power n. Okay, whole power n. If I put n equal to 0, anything per 0 will become 1. So n equal to 0 to, or n equal to 0 to infinity. Okay, then here we are having minus 8 by 3 of, same way, summation n equal to 0 to infinity, since plus and minus are appearing alternatively, minus 1 power n z by 3 whole power n. Okay, now the sum is over, but we can further simplify. we can further simplify it. So how can we simplify it further? That is equal to 1 plus 3. We can take minus 1 power n commonly. So summation of, okay, we can 1 plus summation n equal to 0 to infinity minus 1 power n commonly, so that we can get z power n divided by, see, I am having this 3 also, we are having 3 also, so 3 z power n divided by 2 power n plus 1, then minus 8 z power n divided by 3 power n plus 1. So I am going to simplify it very further. So f of z equal to 1 plus summation n equal to 0 to infinity minus 1 power n, then z power n we can write here also, z power n into 3 divided by 2 power n plus 1 minus 8 divided by 3 power n plus 1. So this is our required expansion. So this will be the Taylor series expansion also. This will be Taylor series expansion also to represent that function. Okay, but we have not used any formula of Taylor series. We have simply used the binomial series expansion. I hope you all understood the problem and enjoyed the problem. Thank you all for watching this video. We shall meet on another problem on another day. Thank you all once again. Okay.